SwayamPrabha. Digital India. Educated India.
Good morning, everybody. Today we will discuss about unsteady state conduction in an infinite slab. Basically, this is analysis of transient conduction in a rectangular geometry with convective boundary conditions. Y and Z dimensions are infinite, and we can see the variation of temperature, or we will analyze variation of temperature in the x direction of this slab. X direction is finite. Now, the local ambience is at a temperature T infinity, and temperature at the surface of this slab is not known, but film heat transfer coefficient H is known. And the initial temperature of the slab is higher than the ambient temperature. Rather, I would say much higher than the ambient temperature. It is being cooled. Now, governing equation is one-dimensional unsteady state conduction equation. That means del temperature del time equal to alpha del 2t del x2, and the boundary conditions are, since we can see symmetry about the midplane of this geometry, so at x equal to 0, del t del x equal to 0 for t greater than 0. At x equal to L, minus k del t del x equal to h t minus t infinity. This is the energy that is being conducted, and the same energy is being convected for t greater than 0. At t equal to 0, temperature is T naught everywhere. X greater than equal to 0, less than equal to L. Now we substitute theta as t minus t infinity. Then the equation can be written as del theta del t equal to alpha del 2 theta del x square. And the boundary conditions now become at x equal to 0, del theta del x equal to 0 for time greater than 0. At x equal to L, minus k del theta del x equal to h into theta. Convective boundary condition, again for time greater than 0. And time t equal to 0, theta is theta 0, and within the domain, and the domain length is x greater than equal to 0 and less than equal to L. So this is the description and the physical understanding of the problem. So again we apply separation of variables technique, and the solution is product of two functions. One is dependent only on x, another is dependent only on time. Then the governing equations may be rewritten as alpha x double prime gamma equal to x into gamma dot. Or we can write gamma dot is derivative of gamma del t, time dependent part of the temperature. So gamma dot divided by alpha gamma equal to x double prime by x, and that is constant, and this can be plus minus both. Separation constant is given by lambda squared. Now if you recall our previous analysis, since the temperature is decreasing with time, the solution which is basically arising out of time dependent part will have this form C1 e to the power alpha lambda square t minus. So minus lambda square as the separation constant will fulfill this condition. So gamma equal to C1 e to the power minus alpha lambda square t, and C1 is any arbitrary constant. Then the other part, that means x double prime by x equal to minus lambda square is the other part of the solution, and from there we can get the x dependent part, which is the spatial part of the function, which will finally contribute to the solution of temperature. So this is given as C2 cos lambda x plus C3 sin lambda x, where C2 and C3 are arbitrary constants. Now, as we have already mentioned, that theta will be basically product of x dependent part and t dependent part. So x into gamma. So this is then gamma part of the solution is C1 e to the power minus alpha lambda square t, and the x dependent part of the solution is a cos lambda x plus b sin lambda x. So this was originally C2 cos lambda x plus C3 sin lambda x. When it is multiplied by C1, so we coin new constants a and b. So del theta del x is now given by e to the power minus alpha lambda square t. We get here minus a lambda sin lambda x plus b lambda cos lambda x, simple derivative, and we substitute the boundary condition, that is at x equal to 0 del theta del x equal to 0 for t greater than 0. And if we substitute that for t greater than 0, so this is not getting affected, x equal to 0 del theta del x equal to 0, which will give us the obvious choice b equal to 0. So now theta becomes e to the power minus alpha lambda square t into a cos theta. And then again we'll apply basically the other boundary condition. So what we are doing, we are finding out derivative minus k del theta del x, which is from here we are getting plus k lambda into a and sin lambda x e to the power minus alpha lambda square t. E to the power minus alpha lambda square t is untouched. Basically, a cos lambda x, we find out the derivative and multiply it with minus k, we get this quantity. This is equal to h into theta. So k lambda a sine lambda L e to the power minus alpha lambda square t, that is the value of minus k del theta del x at x equal to L, equal to h. Theta is a, theta at L is a cos lambda L e to the power minus alpha lambda square t. So from here we get lambda tan lambda L equal to h by k, or we can multiply with L both the sides, lambda L into tan lambda L equal to HL by k. HL by k is BO number. In French it is BO, in English it is Biot. Whatever you prefer, you can pronounce that way. So it is BO number or Biot number, named after famous scientist, famous mathematician BO, who worked on these thermal problems related to conduction heat transfer and also convective heat transfer. So I mentioned about it in the about by BO's work in the introductory lecture. Anyway, so this is BO number or Biot number. Now from here we can write beta, tan beta is BI, Biot number, where beta is lambda L. So this is our final equation, equation 2, or equation 3 we can say now. Beta, tan beta equal to BI, where beta is lambda L. This equation is a transcendental equation and it has infinite number of roots. You can see this is basically tan beta versus beta plot, and then the eigenvalues are basically, you can see beta 1, beta 2, beta 3. These are the points of intersection with this line BI by beta. And these are also, these eigenvalues are also available depending on the value of BO number, beta. These are also available in tabular form. Once beta n equal to lambda n into L, that is known, then lambda n is also known. And we can get the solution in the form of theta equal to summation n 1, 2, 3 up to infinity an, it's a series, cos lambda nx e to the power minus alpha lambda n square t. Now initial condition is known when temperature is T0 everywhere on the slab. So at T equal to 0, we can say theta equal to theta 0. Now theta 0 equal to summation over this series, and this is an cos lambda nx at T equal to 0. So we can write here, after having obtained this form, we can apply the properties of orthogonal function. So within the domain dimension, between the lower limit and upper limit, theta naught, we multiply this by cos lambda mx dx, and also we multiply this by cos lambda mx dx. And we know the property of orthogonal functions is such that when m equal to n, then only it will have non-zero value. Otherwise, when m not equal to n, this will produce 0. So we can write 0 to L theta naught cos when m equal to n lambda n x dx 0 to L summation n cos square lambda n x dx. We perform this integral theta naught sine lambda nx by lambda n upper limit L lower limit 0 n by 2 into integral 0 to L cos square lambda nx is basically 1 plus cos 2 lambda nx by 2. So we perform this integral, and again we have repeated that step to memorize it, that basically we are performing this integral n by 2 0 to L 1 plus cos twice lambda nx dx, and we perform the integration again and set the upper limit and lower limit, and then we find out the value of an. It is given by then simple algebra 4 theta naught sine lambda n L divided by twice lambda n L plus sine twice lambda n L. And we can write it in a more compact form. If we substitute beta n equal to lambda n L, then a n equal to 4 theta naught sine beta n divided by twice beta n plus sine twice beta n. So this is the final form of an in the series, which is the solution. So basically now we can say theta equal to n equal to 1 to infinity 4 theta naught sine beta n divided by twice beta n plus sine 2 beta n into cos beta n x by L into e to the power minus alpha beta n by L square t. This is lambda n square t. So beta n by L square t. And beta n is lambda nl. We also observe from here that theta by theta naught becomes a function of beta nl. That means we can say beta n, which we can say lambda nl. Then alpha, this is t by L square, in addition to beta n, which is basically lambda nl. We have already written it's a function of lambda nl. Then it becomes it also becomes function of alpha t by L square, and it becomes a function of x by L. And alpha t by L square is Fourier number. Again, like Biot, the French pronunciation of Fourier is Fourier. So you can also call it Fourier number, but usually we are not habituated with Fourier. So better to call it Fourier number, because we everywhere use, Fourier series, Fourier transform, and, many other mathematical relations named after Fourier. So let us call it Fourier number. So from 2, we have already seen lambda L is basically function of Biot number or Biot number. So that means this problem of temperature distribution is basically a function of Biot number or Biot number, Fourier number, and x by L. Now, Heisler, another heat transfer scientist, showed that this finite series that is given by equation 5 converges rapidly, and that for the values of lambda t by L square greater than 0.2, all terms after the first can be neglected. So this is a convergent series, and alpha t by L square, that means Fourier number greater than 0.2, all terms after the first term, that means lambda 1L, can be dropped. There is no change. So one needs to know only the first eigenvalue of equation 5. Using this fact, equation 5 reduces to theta by theta naught equal to 4 sine lambda 1L divided by twice lambda 1L plus sine square twice lambda 1L into cos lambda 1L into x by L multiplied by e to the power minus lambda 1L square alpha t divided by L square. So this is, we can say, the final solution. Now setting x by L equal to 0, that means at the center line of the slab, we have the dimensionless temperature, we get the dimensionless temperature at the center line. Obviously, if we set x by L equal to 0, we will get dimensionless temperature at the center line. So theta at x by L equal to 0 by theta, this expression is reduced to 4 lambda 1L divided by twice lambda 1L plus sine square twice lambda 1L into e to the power minus lambda 1L square alpha t by L square. And if we divide equation 6 by equation 7, then we get another important relationship, that is theta divided, theta means this theta anywhere, divided by theta at x by L equal to 0. That means theta anywhere in the slab divided by, anywhere in the slab means at any x in the slab, divided by theta at x by L equal to 0 at the center line equal to cos lambda 1L into x by L. So these three are the final conclusions, 6, 7, 8 of our analysis. Thus, the ratio of temperature at any point in the slab to the temperature at the center line is independent of time. That is given by equation 8. Consequently, the complete temperature history in the slab can be drawn into two charts. These two charts are called Heisler charts, named after the well-known scientist M.P. Heisler. In one chart, the dimensionless centerline temperature is plotted against the Fourier number with the inverse of the BO number as the parameter. So this is x by L at 0, theta at x by L equal to 0, theta at center line divided by theta naught, that means initial temperature minus the final temperature T at the surface. So this is initial temperature. Sorry for this mistake. This is theta at the center line x by L equal to 0 divided by initial temperature, that is T naught, which is uniform over the slab, and when we convert it into theta, basically it is T naught minus T infinity. T infinity is the local temperature. So T naught minus T infinity is theta naught. That means this is initial temperature, and this is temperature at the center line, and this evolves with time. So this axis is alpha T by L square, Fourier number. So with time this will change, and this parameter we can see this is inverse of BO number. Here it's in the decimal points up to 1. Here it's up to, we can see 18. It goes up to, even higher value. Here it goes up to 100. So basically this is inverse of BO number. And this is variation with time, non-dimensional time is this axis, which is given by Fourier number. And the central line temperature will change, and this is the initial temperature. So in the second chart, the dimensionless ratio of the temperature at any point in the slab and the central line temperature, whatever is the central line temperature we get at a given time. Here we get that central line temperature taking this as the denominator, and theta at anywhere, any x location in the slab can be obtained if we plot, or that part of Slab chart where theta by theta at x by L equal to 0 versus x by L has been plotted, and again inverse of BO number has been kept as a parameter. So this is the second part of Slab chart. So combining these two charts, if we know the starting time and then the final time, when we want to know the temperature distribution, we can use this chart in combination with this chart in order to know temperature at a given time at anywhere within the slab, at any location within the slab. So basically, as we have already found out, theta by theta naught given by equation 6, theta at x by L equal to 0 by theta naught given by equation 7, and theta by theta at x by L equal to 0 given by equation 8. These are the final conclusions, and those are summarized in the form of these two charts, which are called Slab charts. And by making use of these two charts, we can find out temperature at any location within the slab after a given time, in the sense that we start with the temperature distribution on the slab, uniform temperature, and after a given time, it is being cooled from both the sides. After a given time, what should be the temperature within the slab at any x location? So the corresponding analytical solution for the one-dimensional unsteady state temperature distributions in a long solid cylinder or a solid sphere, initially at a uniform temperature and subsequently subjected to a different ambient temperature, can be obtained in a similar fashion. So what we did for the infinite slab, that can be extended to a long solid cylinder or a solid sphere in a similar fashion through a similar mathematical analysis. And Slab charts are also available to determine the temperature distribution on those geometries graphically. I am thankful to you. Thank you very much for your attention. Thank you.